Okay, so as Nick mentioned in the previous discussion on feedback loops, one of the main uses for feedback loop is to get the robot from point A to point B on the field. But to do that, we need to know where we currently are. So that's what we're going to go over today. It's a process called odometry. Yeah, that's what it's called. So we have a robot. It will be represented by this box. This robot can be, of course, move in any direction. We'll say it can move forwards, backwards, left, right, and rotate. So to track its position, the first thing we're going to do is we're going to add 3 wheels to the robot. It has its normal drive wheels, but we're not going to use those. And the reason we wouldn't use those to track its position is because they can slip. If the robot accelerates, it gives powers to the motor. The drive wheels could slip a little bit before they actually gain traction and the robot moves. You could, of course, accelerate slower to try and mitigate that, but it's never really going to be perfect. So we prefer to add 3 separate unpowered wheels, which we will call tracking wheels. And those unpowered wheels, of course, won't have a motor on them, but they will have something called a rotary encoder on them, which just measures how far they spin. It's a rotation sensor. So and we will put those wheels here, here, and here. Now we'll go over specifically why we do that in a little bit, but the main purpose is we need 2 that are parallel with each other, that are offset, and then 1 that is perpendicular to those 2. They could be in any position. So for example, I could put one here, I could put one, I don't know, here, and I could put the other one there. That would work perfectly fine, but it's easier to demonstrate if we have them in a more same configuration. Which would be just here, here, and here. So, using those 3 wheels, how do we track their robot's position? Well, I'm glad you asked. So, I'm going to erase that now. And just draw the left and right wheel. We're going to ignore the back wheel for a moment. So I'm just going to draw the left and right wheel. We have the left wheel. We have the right wheel. And so for now we're going to say the robot can't slide sideways, which would be what the back wheel helps account for. But for now we're just going to say the robot can't do that, and of course we'll get to it later. The fundamental theory here is that we can approximate any movement the robot does over a short time interval, so as fast as it can measure. We can approximate it as an arc. So you can take essentially an infinite series of arcs and form any path that the robot traveled. Of course, we're in the real world, so it's not going to be infinite, but it's going to be as many as we can, so as fast as the CPU can churn out these calculations. So what's important here is that these calculations happen over essentially a small time interval. We're going to have the location, or we're going to have the values of these wheels a millisecond ago, and we're going to have the values of these wheels now. And that's what we're going to do the math based on. We're going to figure out how much it moved in that millisecond, and then we just keep doing that, accumulate it to get our position. So let me just draw some arbitrary arc starting from these 2 points. So we have an arc. It's just the path that the 2 wheels would follow over that time interval. This is just an arbitrary path. But for this, of course, we assume it's a perfect arc, which is, you will get some error in the system, and that's where it comes from. If you're not measuring fast enough, and your robot, instead of doing that, did something like that, you could end up reading the exact same amount, like assuming it was an arc, and your position would be slightly off from where you thought it was, but I digress. So we take these 2 arcs, and we know they share a center point. And the reason we know that is because these 2 wheels are parallel. The robot physically had to turn around one center point, so they kind of have to share the same center. I don't really have a much better way of explaining it, unfortunately, but they do. They share a center point. Because if they didn't, they would end up measuring different angles. So hold on. Let me just draw a dashed line there and a dashed line there, just to represent the start and finish. Cool. So this angle, I'll call it alpha, is going to be the amount the robot turned. So the robot did that, it turned alpha. And that's the reason they have to share the same center point, so you need the same alpha for both, because they're physically both on the robot. So yes, you know another constant you need for this, or I guess a constant, is the distance between the left and right wheel. So you can either measure that or calculate that, or you can go through a few processes, but you need to know that distance. It's a physical measurement of the robot, so you can get that fairly easily. So you can, well, we're just going to call that W. And our end goal for our calculations here is going to be calculating our displacement, which is just going to be that. We want to calculate that straight line, which I'm going to call H. Because you can imagine, this is the starting point of the center of the robot, that is the ending point of the center of the robot. That's what we want to know. So our goal is to calculate H. Well, how could we do that? What values do we know? Well, we know how far the left wheel traveled. We'll call that L. We know how far the right wheel traveled. We will call that R. And so those are just going to be the distances that the left and right wheel traveled in inches. Of course, encoders don't return inches, they return degrees of travel, but it's pretty trivial to convert from how far a wheel spun to the actual distance covered. It's just the number of ticks per revolution of the wheel. So it's the number of ticks it measured divided by the number of ticks per revolution of your encoder. If it was degrees, it would just be 360. Multiplied by the circumference of the wheel, and that will just give you how far said wheel traveled in whatever unit your circumference was in. Because Vex uses the imperial system for basically everything, we're just going to use inches. So L and R are going to be the distances the left and right wheel traveled in inches. We know the width, so we have to calculate H. Though actually first, we're going to start by calculating alpha, the amount the robot turned, because that's the starting point. So, cool. What do we know? Well, what is helpful to draw out are the radii of these arcs. So I'm going to just call this little r L. This is going to be little r R. Because they're the two radii of our arcs, and if you notice, our R equals our L plus W. Okay, so that's one equation. Something else that we know is we know that the arc length of a circle, so L is an arc length of not a circle as I've drawn it, but it's an arc, it's part of a circle. So the arc length of part of a circle is equal to the radius of that circle, so our L, multiplied by the angle it covers, which is just going to be alpha. And so we know the same thing for the other one, so R equals R times alpha. So here we have three equations. We have three unknowns, because we know L and R, we know omega, and we want to find alpha, RR, and RL. Really, alpha's our goal, but we'll end up with RL.
We know W?
Yes, and we know W. So yes, three equations, we have three unknowns, so we can solve this. You can do it just by substitution and rearranging. So take this equation, subtract this equation, so we get R minus L equals R. And then we R minus RL, substitute that in here, we get R minus L equals alpha or W, divide by W, we get alpha equals R minus L over W. So that will give us a fairly simple equation to get the angle that our robot traveled over that short time duration. Now, a side note here, while this doesn't prove it, you can experimentally clearly see that this is actually a state function, meaning that if you start the robot at any point, reset your left and right encoders, so they're 0, then move the robot however you want, doesn't have to be an arc, you will get the angle relative to the starting position. This doesn't prove it. This, of course, assumes it's an arc, but it does actually work. You can experimentally see it, and it does kind of make sense. Okay, so I'm actually going to switch colors now for a reason that will be apparent eventually. But now that we have alpha, we can start trying to find h. So how might we do this, one may ask? Well, let's find out. So we can start by splitting up this triangle into two triangles. So now we have right angles. Because right angles are nice. I like right angles. They make math easy. So we have a right angle here, and of course a right angle here. And that means each of these angles are just alpha over 2 and alpha over 2. So we can take this. We know what RL is. We know what W is, or really in this case we care about W over 2 to get to the center. But instead of that, I am actually going to take W and split it up slightly. So instead of having W, we're going to have two measurements, WL and WR, and just for notes up here, W equals WL plus WR. But the reason we would do that is, let's say our wheels aren't perfectly centered on the robot, but we still want to track the center of the robot, we might have a different measurement for the left and the right, because the center does of course matter for what we're about to do. So we know this distance from here to here. That's just RL plus WL. So that's our hypotenuse of our triangle. We know an angle in the triangle, because we know alpha, so we know alpha over 2. So it's fairly trivial to find this side length. So we get h over 2 is equal to RL plus WL multiplied by the sine of 2 alpha over 2. Make sense to everyone? Okay, and so we can just get h equals 2 RL plus WL sine alpha over 2. And now we actually haven't calculated RL yet, but we can easily get an equation for it. So just rearranging this one, we can get the RL equals L over alpha. And so we can just sub that in. We get h equals 2. I'll just say L over alpha. L over alpha plus WL sine of alpha over 2. So that gets us h. That's the distance we traveled. We have the angle we traveled. That's basically all we need. That will give us our displacement in polar coordinates. So now we have this, but what do we do with it? Having just the amount the robot traveled over a short distance relative to the starting position of the robot doesn't really help us. So now we need to take this and change it into field-centric coordinates. So if we have our field here, so let's say we have our field, that's a square, trust me. We can designate a x-axis, we can designate a y-axis to the field, and we'll call the bottom left just 0, 0. So we have our field, we're going to call this down here 0, 0, just the bottom left. So if we had any point on the field, we would have a x-coordinate and a y-coordinate. Kind of makes sense? Yeah, okay. So the robot will have started at some coordinate. So let's just draw kind of like that. And then it will have traveled along some arc to some finish point. We know the point where it started because we've been doing this calculation up till now. And from the start, we always know where we start. That's one thing we just have to put in. So whenever the program starts, it needs to know where it started. So at the beginning of autonomous, it would set its position to what we program in, because that's always going to be the same. Or change based on what autonomous we will run, but you get the point. That's known information. So we know the point where we started, we know how much we moved, and we want to figure out the ending position. So let's do that. So we have where the robot started, we have an arc, more squares where the robot ended. So we know that, and then we know, what do we know? So we have H. Okay, we're going to call, so that's the robot starting, that's equivalent to, okay, so we know, here's what we know. We know that angle, which is equivalent to alpha over 2. Why is that equivalent to alpha over 2, you may ask? Well, either you can just look at it and see it. If you can imagine this line shrinking, that line would go like that. They kind of act the same way. So we have this triangle here. So the angles have to add up to 180. This angle equals 180 minus 90 minus alpha over 2. So that's just 90 minus alpha over 2 for this angle. And then these two angles have to add up to 90. So we get 90 minus, and then what was here from before, this angle, 90 minus alpha over 2. We get this is alpha over 2. So we get that angle is alpha over 2. And physically represented here, that's going to be this angle. That's alpha over 2. And the reason it's that angle is because we have the distance from the start to the finish, which is that one. And then we have the robot's like looking forwards point from the start, which is that. So that angle is alpha over 2. So what we want to calculate is, so now let's say these are our field axes. So this is y and x. So we got x, y, both positive in that direction. Also, for just one thing to note is we're doing the counterclockwise positive convention. As you can see here, we turn counterclockwise, we've got a positive angle. Well, if you can imagine it. Where's my formula? Right, yeah, so here it's counterclockwise. L is less than R. If L is less than R, we get a positive value. If it turned the other way, L would be greater than R, we'd get a negative angle. So that's just following kind of standard math with counterclockwise positive. So actually, we'll draw that as well. So we know that this distance, which we called h. We want to calculate the robot's displacement relative to the field. So we want to get its delta, not a delta, delta y and delta x. So how are we going to get those, you may ask? Well, you see, another thing we know is the starting angle of the robot, just as well as the starting position, which we know because we're right here. We know the starting angle. So assuming we, again, follow convention and go this being 0 right here, we would know this angle, which we will call theta. So that's another piece of information that will prove mightily useful. I'm going to redraw it. So this is our delta x, this is our delta y. As you can see, they're the exact same values from before, but now we have the angles inside the triangles. That makes it easy. So we have the hypotenuse of the triangle. We have one angle of the triangle, which is just alpha over 2 plus theta. We can calculate our delta y and delta x. So we can get delta x equals cos, or well, h, there we go, h cos theta plus alpha over 2, and we get delta y equals h, so that is h sine theta plus alpha over 2. So that's our delta x and delta y relative to the field. So then at the end of each cycle, we would just go theta plus equals alpha, x plus equals delta x, and y plus equals delta y. And that, running quick enough on our processor, would get us the position of the robot. Mostly. In this, we assume that the robot could not slide sideways, because we just did an arc. In theory, it could be an arc while sliding sideways, which you'd think would make things more complicated. It really doesn't. It's actually quite trivial. So I'm not going to go over a full proof for it, but what you do is, if you notice in our math, we calculate the angle. But then after that, we only ever look at one of the two sides. Here, we only ever look at L. We never actually touch R, like at all. And we could do the formulas in the opposite and only ever look at R and not look at L. And so what we do is we take all this math in red and blue and do it again, but using the alpha we calculated with R and L, and then just use the back wheel instead of L, and instead of WL, we use the distance from the back wheel to the center. So let's say we had our robot. We have our left wheel, we have our right wheel, we have our back wheel. We're going to have, I'm going to call the back wheel just S. So we have L, R, and S. We have W, L, W, R, and W, S. So you just take these equations, replace WL with WS, and L with S. Swap X and Y here, because it's pointed in the other direction, and just add those on to here as well. And that's it. That's all you have to do to account for the robot sliding sideways. Does that kind of make sense to everyone? Anyone have any questions, any comments, concerns?
Wait, what situation would there be where the robot would be sliding sideways?
What's the P1?
So I'm just going to take an X drive for this because it's the easiest example. Let's say we had our drive down here, starting in this position, and we wanted to move to this position. The fastest way to do that would be move and turn at the same time. If you can imagine that, so we're turning, so we're traveling through an arc, and if we're moving not perfectly forwards, backwards, or left to right, we'd be traveling at some diagonal. So that would have to be sliding sideways, per se. Anything that's not just straight forwards and backwards on some forwards and backwards arc is going to incorporate some sliding sideways. So a normal drive with just your normal 4 omnis can't forcibly slide sideways, though if you do go forwards and turn with some momentum, it will end up sliding sideways because you're all omnis. Now you could replace them with some traction wheels and we can get into that. But another robot could push you sideways. So then you're uncontrollably sliding sideways. So it's nice to be able to track that, and it's usually not that hard to add the third wheel. So